So yeah, all you can do here, because to get the inverse Laplace, there is no s cubed in the table, as you can see. You'd have to factor it further. So yeah, for this one, I could factor it. I could factor out an s, and this becomes s squared plus 2, and this is s plus 1. Now this is no longer factorable. Now you have to do partial fraction decomposition. So you'd have to split it into a over s, if you remember from pre-calculus or calculus 2, whatever. And then this here will be an s squared plus 2. So if you remember, in this case, the numerator has to lag 1 degree behind the denominator. So if now it's an s squared, here you need a bs plus c. Okay? And now you have to take a common denominator, which of course will be the original one, s times s squared plus 2. And a multiplies the s squared plus 2. And the bs plus c multiplies the s. And now, of course, you set that equal to the original. S plus 1 over s times s squared plus 2. And now the denominators cancel out because they're the same. And now the objective is to go after the a and the b and the c, to find them. Yeah. And the way we're going to do this is we'll FOIL this here. So so I'll do the right hand side first. So this is a s squared plus 2a, right, plus bs squared plus cs. So I FOILed these. And this, of course, has to equal to the left-hand side, which is s plus 1. And now I collect the s squared together. So this is a plus b times s squared. And I collect the ones that have s together, which is just cs. And I collect the one that doesn't have an s, which is just the 2a. And I set that equal to s plus 1. Now, I don't have any s squared on the right-hand side. If those two polynomials ought to be equal, their coefficients have to be the same. So that just means a plus b has to equal 0. It also means that this has to equal this, which makes the c equals 1. And it also means that this, oops, this has to equal this. So that just means 2a equals 1, which makes a half. And b is just minus a. So b is minus half, according to this equation here. So now we found the a, b, and c. Now we take them and we plug them back here. Okay, so this becomes a over s. So a over s is the same thing as saying half times 1 over s plus bs plus c. So that's minus half s plus c plus 1 over squared plus 2. And now what I need to do is I need to take the inverse Laplace of all this, which means I can take the inverse Laplace of the first one, and the half is a constant, so I can pull it out, plus the inverse Laplace of minus 1/2 s plus 1 over s squared plus 2. Okay, So let's take a look at each one of those separately. The first one is easy. 1 over s is just, if we look back in the table, 1 over s is a unit step here, yeah?
Yeah.
So that's just 1. If you look in your table, 1 over s is just 1. So the first part of this is just 1/2 times 1. Okay, plus. Now the second one, we would have to further simplify it. Right? Let's see how we're going to simplify this. So what we could do, because you see s squared plus 2, I have here an s squared plus. I just don't have the numerator matching, yeah? So if you look at 11 or 12, wherever I have an s squared, I either have an s or an a on top. I don't have two things, so it might pay off to separate this. So this is minus 1/2 s over s squared plus 2 plus 1 over s squared plus 2. And now I can take the inverse Laplace of each one of those separately. And this minus half is a constant. I can pull it out in a second. Right? And so we need s over s squared plus a. And if you look here, s, so we have s over s squared plus 2, yeah? So this is number 10. S over s squared plus a squared. Because I could rewrite this here
That's s squared.
as root 2 squared, because root 2 squared is a. So the minus half comes out. Let's write in green here. So we have so far a half coming from the first one plus. So the inverse Laplace is, so I can pull out the minus half. And s over s squared I just showed you, plus b squared, where b is root 2 in this case, right? Is cosine bt. So this becomes cosine root 2t, according to the table. Or cosine at, and in our case, cosine a is just root 2. Alrighty? And the last one is 1 over s squared plus 2, so that a over s squared plus a squared, that's number 9 in the table, because I could rewrite this as the a is 2, or a squared is 2, right? So I could rewrite the 2 as square root 2 squared, but I also need a square root here, 2. So what I can do to manipulate this, I can multiply here by square root 2 and divide here by square root 2 to make them match, because it has to match the table a over s squared plus a squared. And the first 1 over root 2 can just come out. This is just 1 over square root 2. And the inverse Laplace of root 2 over s squared plus root 2 squared, that is just sine at where a is root 2. So sine root 2t. So this is the inverse Laplace transform of your function, but using partial fraction decomposition. Okay? Partial fraction decomposition. So we used partial fraction decomposition to decompose the function so we can put it in a form that we have in the table so we can find the Laplace transform, the inverse Laplace transform. Okay, that's how you do this one. Questions on this one, man?